Okay, now, yeah. And then I explained that Lorentz transformations can be represented by 2 by 2 matrices, okay? Okay. And these matrices, these matrices are 2 by 2 matrices, are 2 by 2, and have determinant equal 1. So they are SL2C matrices. And from now on, okay, Lorentz transformations will be represented in this way, SL2C transformations. Then the fundamental representation of SL2C is left-handed spinner, okay, and then which I denoted by chi with lower index alpha, and under Lorentz transformations, this transforms, as I said, into fundamental representations, okay. And then similarly, we constructed conjugate representations, and we introduced dotted spinners, okay, and which transform with Hermitian inverse matrix. Okay? All right. And then in the next step, I constructed Lorentz invariants, and these are these angle and square products. So for two spinors like that, invariants are constructed by contracting these spinorial indices. And that was denoted by an angle. It was an angle product. And for complex conjugate, the convention was that the contraction was like that. For complex conjugate, for the dotted indices, we transformed them. They were contracted top to bottom, and that was 1, 2. Okay, all right. And then, okay, so that holds for any spinner, but then I specify to the very important case of so-called momentum spinners, which satisfy Dirac equation, and which satisfy Dirac equation, and I constructed the solutions of Dirac equation, and I constructed them by solving Dirac equation in some simple frame in which particle is moving, massless particle was moving in one direction, and in one direction, and then I boosted it, and in this way I constructed these momentum spinners, and the notation was that the spinners were represented again according to the notation. This was like a spinner, momentum spinner corresponding to a given momentum, light-like momentum P was denoted like that. Then the alpha opposite, and then raising and lowering just was changing the direction of from brat to cat, and vice versa. And okay, and then here, that was like that. It was like that, and then lambda para with upper index. And this is, as I explained before, I raised lower by applying this 2 by 2 antisymmetric Levi-Civitas symbol. Right? Okay. And then there was another thing which I told you that also, since we want to use this SL2C as really to represent Lorentz transformations, vectors will be also represented by spinners, and for that, what we have that from having vector V, we construct a 2 by 2 matrix, and also we can construct conjugate matrix by contracting with the sigma bar matrices, okay, which I explained how they're constructed. All right? And then if you apply now for a specific case of momentum P, then of these matrices represented like momenta, then we had the notation was that P matrix was so that this is one index like that, P, and then like that, P. Okay? This is a bracket. All right. So that was essentially all what I needed last time, what I need to go on now. And I want to go back to this construction of the momentum spinner, which is solution of the Dirac equation. By performing this Lorentz transformation to transform particle, which is moving along the z-axis, into a particle moving in arbitrary direction. So now, from that, I told you that when I started from Dirac solution of Dirac equation, and again in this frame in which particle is moving with momentum p0 and pointing in a z direction. And what I did, I transformed this arbitrary momentum p, and this way I obtained obtain a solution for arbitrary momentum. Now, the point is that when you have a fixed momentum, they're both, of course, the Lorentz transformation doesn't change p squared. You have both like momenta. You have one momentum which is pointing in the z direction, and then you want to perform Lorentz transformation, the momentum pointing in the other direction. What you do, to do that, it's sufficient to use 3 parameters. It's sufficient to rotate by using two rotations. The vector, so it's the 2 vectors that this original vector points now in the desired direction, and then you stretch it by boosting. That means that there are 3 remaining parameters which are not used, yes? Which means that the momentum vector is invariant under 3 Lorentz transformation, yes? One of them is sort of obvious, yes? One of them is a rotation about we are pointing in the z direction, yes? You rotate in the direction of motion of the particle, yes? Okay? And there are 2 others, which you can construct explicitly. So this one rotation, when you rotate about the z-axis, then you see that that the Lorentz matrix looks like that. So that you see that lambda 0 has quite as a phase. Yes, it's a lower component. So that means that this momentum spinner represents a particle with spin equal -1/2. Yes? All right? So, and then the same thing when you transform this particle so that it moves in the desired direction, you can still rotate about direction of motion, and you'll get the same phase. Okay, which means that these spinners represent particles which have spin aligned with the direction of motion, 1/2. So this is helicity, yes? So these undotted momentum spinners are wave functions that represent massless particles with a negative helicity -1/2. So that's why they're called left-handed. For some people, they're called right-handed, but we'll call them left-handed. Okay? Same thing when you transform, of course, you take lambda bar, you transform with the plus, yes? It means that it has helicity plus 1/2. Right? So that's what we are. Okay, then these two additional, so this is one rotation about the momentum direction. There are two other transformations which you can write explicitly. The point is that they do not change the momentum spinors. By the way, it's trivial to see that that such transformations do not change momentum in this notation, because I told you that this momentum matrix is simply written as this way. Okay, which means that these phases cancel and the momentum does not change. You see that explicitly. Then there are two other transformations, as I pointed out, you can identify explicitly, and you find in addition to the rotation, you get two transformations, okay, which are combinations of rotation and boosts. They do not change the momentum spinors. And if you look at the algebra of those transformations, you find that, that this group is isomorphic to the symmetries of two-dimensional plane, which is E2, yes? Which has one rotation and two boosts. And this group is called Little Wigner group. Not Wagner, Wigner group. Okay? All right, so it's Little Wigner group. Now, this group will play important information because, again, these rotations, these little rotations of a Wigner group, they can determine helicity particles, and that actually they will be important for discussing general properties of scattering amplitudes, because these momentum spinors and then polarization vectors, which I will construct in a moment from those momentum spinors, will enter as wave functions and Feynman diagrams. Right? Okay. Good. So now we will, from now on, now I will start discussing amplitudes and general properties of amplitudes. Okay, so okay, so in general, what you are computing some transition, some S-matrix element, scattering amplitude, which tell you have some number of incoming particles, which carry certain momenta, okay, helicities, and some gate charges, yes? And so we have some number of particles in the in state, and then you have some number of particles, okay, and out state. I should put, out. I should put it like that. Okay. Now, the basic property of S-matrix is crossing symmetry. Crossing symmetry tells you that in order to obtain one of consequences of crossing symmetry, that in order to obtain a scattering amplitude, which you have is so that in order to compute scattering amplitude for a particle which is outgoing, instead of that, you can construct an amplitude with antiparticle which is incoming. So in general, crossing symmetry tells you that is telling you that incoming particle in with momentum p, some helicity and some charge a, is you can obtain scattering amplitude. This scattering amplitude is the same as the scattering amplitude for antiparticle with momentum minus p, minus helicity, and of course, okay, it's an antiparticle, so opposite charge. Okay. Okay? All right. So that's why the conventions in the amplitude world is to consider scattering amplitudes, which all particles are either outgoing and or incoming. It's a matter of convention, yes. Well, I can use conventions, for example, that all are out, particle out, and then if you have outgoing particle, then it will be equivalent to incoming antiparticle. And so in this case, of course, the sum of all momenta must add up to 0. So the basic constraint on scattering amplitude is moment conservation. When in these conventions, all particles are out, simply tells you that the sum of momenta is equal to 0 for n particle amplitude. All right? Now, what does it mean in our spinor notation? That momentum I is like that, yes? All right? So you can sandwich it with any spinor L and any spinor K, like that. And then you add up then this will vanish. Okay? So this is the constraint which follows. So this is the constraint, the basic constraint of momentum conservation written now in Helly's notation. Okay? All right? Okay. So that we took care. We have all particles coming out. Another thing is I want to write a general expression for the amplitude. Yeah, I think that I'm done with that. I can write a general expression for this S matrix element between some in and out states. A general form of that, if you learn in a quantum field theory course, that it has I in front, has 2 pi to the 4, and then has a momentum conserving delta function. In this case, is that there's a sum, it's a 4 component, so the sum over all momenta, yes. And then what left here is the real stuff. It's called matrix element, which of course depends on all momenta, Helly's, and gate charges. And this is so-called Feynman matrix element. And you learn in school how to compute it by using Feynman diagrams. Yes? But the whole S matrix element contains, in addition, this this momentum conserving delta function. Okay? Okay. Now, what is important also is to know what is dimension of this Feynman matrix element. Feynman matrix element, okay, that's easy to check, is dimension is 4 minus n, where n is, of course, the number of external particles. Okay? Now, what you do, so this is just what you would call scattering amplitude in the momentum space. Okay? Now, what you do usually, now when you construct so-called Helly's amplitudes, you express everything, which include, in particular, the momenta, in terms of by using this relation, and then everything, the whole amplitude is expressed in terms of those momentum spinors. Yes.
Sorry, is that the mass dimension? Sorry, what was that?
What did you say?
Sorry, what was the? You said dimension of m. What was that? Was that mass dimension?
Mass dimension. 4 minus n. For particle amplitude has for particle amplitude should be 0, yes? So if you see this formula, is exactly dimension 0. So when I'm talking about dimension of the Feynman matrix element, as matrix itself, you have to of course add, add -4, yes, which is coming from the delta function. Yes, but by itself, the Feynman matrix element has always the same dimension. Now, the dimension will be provided by momenta, or eventually, in a theory which has dimensional coupling constant, like gravity, you have to also count the dimensions of the couplings. But the net dimensions will be always 4 minus n. Okay. All right. Next. Now, as I mentioned before, okay, I can go here. As I mentioned before, to compute this invariant matrix element, you compute, okay, you have this process in which you have a number of particles, like fermions, and you have some bosons, like gluons and photons, and then what you do, you can construct them in perturbation theory by writing all possible Feynman diagrams. The Feynman diagrams contain vertices, okay, contain propagators, contain eventual loops, yes, if you wish, yes. But the thing that the important point, then all these propagators and vertices are written in terms of momenta, as you look in a book, yes? Now, the point where there is additional, however, ingredient of Feynman diagrams, is you contract them with external wave functions, okay? So and then I told you that, for example, for left-handed spinner, we'll have contracted that fermion line with this momentum spinner, which has helix -1/2.
I asked, by wave function, do you mean the source, like source? By wave contracting the external legs with wave function, do you mean sources, like Schwinger sources for QED, or?
I'm talking like, take photons with polarization vector.
Okay.
Okay, that's what I mean. Yeah, that's actually what I'll focus now, because I didn't discuss polarization vectors. So what I want to do, so for fermions, actually I won't be talking much about fermions. I'll be concerned mostly with amplitudes involving photons and gluons. And for that, I want to construct the polarization vectors for spin 1 particles. Okay? And now, so to do that, you write the solution of Maxwell's equations in a specific gauge. So what you do, you're already moving to the left time. Okay, that can go now. So we want now to construct polarization vectors. And so what you do, you write down solution of Maxwell's equation as a superposition of plane waves. So let's write down one plane wave. Again, you have 2 possible polarizations, and so again, helices of gluons or photons. And you have positive and negative energy waves. Okay, times AP dagger. Okay. Again, p square is 0, yes? And now these helicity vectors, of course, depend on the momentum p of the photon or gluon, right? So now, what we do is, again, we construct these helicity vectors in the simplest possible frame in which the photon or gluon is moving in Lagrange z-axis. And then, of course, well, you do it in the so-called then it's straightforward to use radiation gauge, which, so that the 0th component, time component of this momentum of the polarization vector is 0. And then just to impose additional constraint is the radiation gauge, in which you have that that it's a transverse polarization. So the scalar polarization is equal to 0. So explicitly, if you can write it with some arbitrary normalization, which is chosen for, okay, I'm using this one, others use another one. So we have a two polarization vector, okay, describing a spin 1 particle, yes, with two possible two possible polarizations, plus and minus 1. Now, one way to convince yourself that it represents as a polarization describing polarized magnetic wave, you compute the electric magnetic fields, and you will see that it's indeed the polarized wave in which electric magnetic fields are spinning, yes, and the left or right direction depending on the helicity plus or minus 1. All right? Good. Now, so as in the case of momentum spinners, I will construct polarization vectors in an arbitrary frame by performing a boost, yes? The same boost as before, the same rotation and boost, Lorentz transformation. Now, to do it, it's convenient to write those constraints in a covariant way. So I have essentially that the first constraint is that the scalar product of the momentum and polarization vector is equal to 0. And then I have the second constraint is, which I can, since essentially there are two 0 components, I can write it this way. Okay? Where R0 is a light-like vector. Okay? Plus or minus 1 here. And then, so I can, since light-like vector, I can write it down in a spinor helicity notation as, okay? And I can also construct, since I can also write it in a similar way like I did before for the momentum, I can write it as introduce as spinors, which explicitly here are just the square root of 2 and 0. And then, of course, this vector, matrix vector, is just the product of R times R bar. Okay? It's completely trivial. Then, these polarization vectors can be written in the following way. You can check it explicitly. In this frame, minus will be okay, 0, the one which I discussed before. And I think that there's a plus 1. And then minus 1 involve lambda bar, and this involve lambda. And again, this is the 0 specified again. This is the one which solves the drag equation in this special frame. Okay? So that's the starting expression. Okay? So now, what I do, I perform Lorentz transformation to the frame in which to the frame with arbitrary momentum, and then it's obvious what is happening, that these spinners transform into now the momentum spinners corresponding now to momentum. Okay, if I call it I call it here P. Yes. While this one also transform to this one also transform to another spinor, which I called R prime. Okay? So this is now, I have polarization vectors in arbitrary for a photon or a gluon which are moving with momentum p. Now, the next step, of course, so this r prime was obtained from R0 by a boost. So you would think that for each photon you have different r. This r is called reference vector. Or these r spinors are called reference spinors. Now, however, there's a very simple exercise that you can show that changing the reference vectors corresponding to shifting the, okay, now these are the polarization vector.
Same brackets in the denominator.
Which one? Yeah, I also have to change them too. This is R, and this is R prime.
I think you're missing beta with lower lambda.
Yeah, this is beta, yeah. Yeah, now we are all set.
The brackets are SL2 invariant anyway.
Huh?
The brackets were SL2 invariant anyway, so you didn't have to change them.
Yeah, but that's, I write it like that. That's correct. Now, the next step is to show, there's an exercise, which is a trivial exercise, that changing these reference vector from r prime to arbitrary r corresponds to shifting the polarization vectors by a term which is proportional to the momentum, in this case, p mu. Now, the basic property of Feynman diagrams that when you replace any polarization vector by the momentum, then the diagram vanishes because of gauge invariance. Okay, so then that means that instead of using this r prime different for all particles, I can choose one for all. Fixed reference vector for all particles. Okay? And this is a trick. These are the, so this representation of polarizations is very convenient not only for computations, because by appropriate choice of the reference vectors, you can accomplish many things. For example, if we have a same polarization vectors, one with momentum p, another with momentum p prime, but with the same, and it's with same polarization, if you choose that trivial exercise, that if you use the same polarization vector for both of them, this will be 0. So a big number of Feynman diagrams will disappear. And that was historically very important for understanding how to compute scattering amplitudes efficiently. Okay? But also, what is even more important is that now you see explicitly, by looking at these momentum spinors, you can explicitly see that polarization -1 is really that this represents particle with helicity -1, because you have -1/2, and this is in the denominator, so it's -1/2. So you see that this, when you perform this little group rotation on a polarization vector, you'll get this phase which will be determined by the helicity. All right? Is it clear? And that is very important. So
Cancelled from denominator?
what about? Yeah, you have to count that. This is -1/2, and this is in the denominator, so it's -1/2. So together, -1.
So it will double.
Yeah. Yeah. So you see, for example, now, I won't talk much about it, the wave functions of gravitons can be simply constructed as products of those spin 1 polarization vector, and you will see that now you will explicitly get a helicity plus or -1, plus or -2. All right? So that's a very important property of Feynman matrix elements. Yes? Now, before, I want to write one formula here, which is, here I'm using the spinors, but of course I can use R, I can use here this angle and square bracket notation, and then then you can write this equation here because I won't be using it again. If you have a vector with polarization vector with reference vector r and dot with any momentum, another momentum, like momentum p. So this is the photon or a gluon, and this is any other particle, other but massless. Okay, then I will obtain that simple expression, which I'll be using, I don't know, today, I'll be using it many times. So I want to write it here. And then when I erase it, you will see that this is completely trivial. It's the same thing, yes? Indeed, when you put here P, yes, you get RP. Sorry, if you put K, okay, this momentum, I changed it because I used for the spin 1 momentum K because then I want to single it out at the end. The interesting case for me will be the soft limits in which K goes to 0, okay? So if I put here, this is K, and this is P, so RK, KP, yes? You see over there. Okay, that's completely trivial. And you see here explicit dependence on as far as K, it has this Helest -1 or +1. All right? And the reference vector is anything you wish. It's up to you. Okay, I can erase that. All right, good. So now, okay, the next thing which I want to do, I'm sort of set up for discussing scattering amplitudes and the properties under this, the transformation properties under little group and so on and so on, okay? But for a reason which will become clear in a second, what I want to do, I want to consider the case of complex momenta, okay? Considering in this context, is maybe not directly related to Whistler theory, but it's, for me, it will be a way of relaxing kinematic constraints coming from momentum conservation. Okay? And you will see how it will happen. So some amplitudes which vanish for real momenta, they will be you can make them non-vanishing if I use complex momenta. Again, these momenta, I'm considering the case of massless particles only. So the momenta will be always light-like, and that if I now can represent them by so that means that if I represent this now I construct these vectors from vectors I construct matrices, then the corresponding matrix will be now still will have a determinant 0, yes, but because determinant of this matrix is always p squared, but that means that the two rows or columns are proportional to each other. So I can always write them in this way, where now lambda and lambda tilde are two independent complex spinors. Yes? All right? Now, under Lorentz transformations, now for those particles, then the one of them will transform M with matrix M, and another one will transform with another matrix. I mean, which I call M tilde. Okay, and so, and then this momentum will transform essentially like under similar, will transform under similarity transformation. Okay, and you see, so now M, so essentially in this case, roughly, Well, you have two SL2Cs, one acting on left-handed and one acting separate on right-handed spinners. Yes?
Do we have some relation between tilde and tilde?
Not yet, no.
Not absolutely.
No. So it's SL2C times SL2C.
Okay.
That part. I need you for a general. It will be it could be GL. The S is coming from that you want to keep the angle product and the bracket product invariant. Okay, because for that you need S. You need determinant equal of M equal 1.
Yeah, but they are just independent representations.
Then independent. The M tilde are independent. You can perform two separate transformations on left and right-handed spinners. Yes, while, of course, before I have just one matrix M. Okay? Now, what about this little group in this case? The little group, now you see that I can simply multiply any this left-handed by some number, arbitrary complex number, and lambda tilde. If I multiply it by an inverse factor, then momentum will not change. So I have a little group which, okay, and now I have just, which involves these rescalings, arbitrary rescalings of the momentum spinners. All right? All right. So here, so suppose that I do that, I compute Feynman diagrams, and then now I want to go to what I want to do now. I want to discuss the properties of I want to explain what happens to the Feynman matrix elements once you perform these type of transformations. Okay? Okay. So first of all, so I'm talking about the matrix element which depends on number of lambdas and lambda tildes. Of course, I explained before, the interior side of the diagram, if you forget about external legs and the wave function, contain the same number of lambda and lambda tilde, yes? Because that's what momentum is. But now, so then, this interior, the vertices and propagator will not matter if, for example, I rescale, okay, I do this transformation, and this which for each particle, I transform with a different, I can transform it with a different factor. Yes. Then what will happen that if I have external particle with helicity HI, yes, if now HI are particles, so this is particle HI, okay? Then from each particle with helicity I, we'll get from this wave function a factor which will be one factor when it's helicity 1/2. When minus 1/2, you see it's minus 1/2. This is will be a factor lambda, which will come just from this left-handed spinner, yes? And then from the right-handed spinner, you get so altogether, and then of course, from the vectors, I told you that you count them. You have effectively this two spinners, so you get always this factor, and so we have for each of them, our factor will be product of that. Yes? So that's very important property of the amplitude. Is it clear? Yes? Okay, because you see from here, for example, okay, now this, I will have, now I replace them by this complexified, so this angle is associated to this, to lambda. Now the angle, the bracket, in the bracket you will have lambda tilde, And so here you have altogether from here you have a T2 minus 1 if the scale is, let's say, if its scale is the minus 1. Yes? For plus, you'll get T2 plus. The T2 minus. The opposite here is T2 minus HI. So that's the first property. Now, there is another property which is very important, is that if I rescale everything by the same factor, yes, then of course, well, it will count dimensions, yes? So if I rescale everything, if I take amplitude and rescale each lambda, since they have lambdas, by the way, have dimension, as you see from here, have dimension, okay, you see that each of them has dimension 1/2.
Shouldn't it be like t times the phase or t to the power?
What do you say?
Like, because the lambdas under the helicity where we perform the rotations, we got that.
Yeah, no, that takes care of the rotations. That is equivalent to rotations. For if you don't use complexify momentum, there is a rotation factor. It will be always the same thing. Okay, I mean, from complexify, I'm using arbitrary t. If you don't do it, then it will be just a phase. Okay. On the other hand, here I also rescale by, if I rescale lambdas, okay, then I told you each lambda has dimension 1/2, yes, because of that. Then what I will get is that if I rescale everything, then effectively I'll be probing the whole, I'll be probing the dimension of the amplitude, yes? And then, of course, if I do it, I have to rescale, of course, and a dimension, there will be some number of dimensional couplings, yes, which will have altogether with up to dimension d, yes? Some total c to some power d. In Yang-Mills theory, for example, in QED, there won't be such a factor because the dimensionless coupling, yes? All right, so now, that will simply the probe dimension. So we see this is, since it was 1/2 dimension, so we see to 4 minus n times amplitude, origin amplitude. All right, okay? So it's a very important, properties from which you can learn much. They contain really very important information to the extent of fixing even some amplitudes. Okay? Just dimensionful, dimension plus this little group transformations will allow us really, will allow discussing the amplitudes. The first case, which I want to discuss, is a scattering of 3 particles with arbitrary helicities, yes? Gluons with fermion, with quarks, you name it, okay? And then what I want to discuss now, the amplitudes, and all 3 particles are massless, yes? So I have, just a second. Yeah.
Is the little group for the complex momentum only 2 parameters, or is it still?
No, then of course you have more, but these are the ones which I'm using.
Oh, okay.
Yeah, like before, you have these combinations of boosts and rotations. Again, this is again, if you were really curious, then you can look into these notes which are listed, which are linked. Okay. Okay. So 3 particles. We have all of them. Outgoing. Yes. 1, 2, and P3. Okay. We have the following constraints. With the constraint momentum conservation. Yes. Okay. And then we have their own shell. Okay. And then there is an addition. Of course, there's a constraint where since momentum conservation, P3 square is P1 plus P2 square. Okay. So that tells you that also all product like P1, P2, P2, P3, and P3, P1 are 0. So essentially, all kinematic invariants are 0, yes? So if you lived in a, so then, of course, if this was, if you thought about this process in, with real momentum, there's nothing, there is no invariant. Okay, the amplitude M should be this scattering, this invariant matrix element should be Lorentz invariant. The amplitude must be 0, yes? But now, you can relax this constraint. You can relax this constraint if you use complex momenta. Okay? And this is done in the following way. This you cannot change, and you cannot change that, yes? Okay, so the only thing, but now, for complex momenta, these constraints look in a different way. So we have that, first of all, 1, 2, so we'll give you that. And then you have this one. Okay, this is P3, P1. This is 2. And this is equal to 0, yes? All right? Okay? This is one constraint, which is just these constraints written in terms of spinors. And then you have momentum conservation. You put here some of, so choose here 1, for example, and 3. And then I told you that you can now sum over this momentum conservation, the sum of that must be equal to 0, yes? But now, of course, from here, 1 and 3 are not here, so all what you get from here is just k equal 2 contributes. So we have another product which is vanishing. And again, there are actually 3 of those products by the same argument. Which is equal to 0, yes? So these are the constraints which you have, which follow just from momentum conservation, from onshore conditions, right? Now, so we want to solve this constraint.
Underline 1 plus momentum conservation, the second.
This is momentum conservation. Because it's sum, if you take any 2, I put 1, 3, and then you sum, we have 3, 3, it cancels here, and so on and so on, okay? All right. So now, I told you before that it's explicit if you look at this parameterization, and okay, you can see this, that actually, if you look now again in these constraints with the real kinematics, then you see that there was that the momenta, that one way of seeing it, that I parameterize lambdas by z, and lambda bars by z bars, yes? So actually, with real kinematics, 1 to equal 0 automatically imply this bracket vanishing implies this bracket vanishing, where it's essentially complex conjugate of the other. But now they're independent because you have lambda and lambda tilde. Yes? So I can choose, for example, I can do the following trick. That will leave me with some kinematic invariants that I can use and construct amplitudes. Yes?
In that second constraint, in the middle one, should there be a 2 somewhere?
Yes, this should be, no, this is 1, 2, 1, 3, 3, 2, yes. Yeah, sorry. Okay, good. All right, so now you can, well, you have to start from somewhere. So from here, you can choose, for example, that being 0. That will take care of that. Well, also let's put 1, 3 equals 0. It will take care of that. I don't have to do anything more as far as this line, because when 1, 2, and being, you can think about it. These you see that these are essentially like a three-dimensional cross products. Yes. So in other words, here it tells you that 2 is parallel to 1, 3 is parallel to 1. That means that 2 is parallel to 3. Yes. So it takes care of that constraint as well. Okay. And then you see that by imposing this constraint and doing nothing to the angle products, I satisfy momentum conservation. So in other words, now I have arbitrary 1, 2, 2, 3, and 3, 1 are arbitrary. Okay? And I can try, and so I can use these in kinematic, I can use these invariants in order to construct amplitudes, yes?
So we extend it to complex momenta and then
Exactly.
kinematic.
Yeah. And now, of course, I can, that is one solution, yes? Another, this solution is called holomorphic solution. I'm left only with the angle brackets. It's called holomorphic solutions because you remember these momentum spinors were parameterized by z, not by z star. Yes? So it's called holomorphic solution. Now, I can do other thing, of course. I can construct similarly anti-holomorphic solution, yes? Okay? And then I leave it to exercise to show that there's no mixed solution, which means I cannot put, for example, 1, 2 equals to 0, and I cannot do it. I can't say that is equal to 0, and that is equal to 0, and then, okay, you will screw up everything. Okay, you have to check it out. So there are no mixed holomorphic, anti-holomorphic. There are only two solutions, holomorphic and anti-holomorphic. So let's stick to holomorphic, and then I try to write some 3 particle scattering amplitudes just using our, and all what I will have to do is to, all what I can do is to use these constraints. So in general, what I can do,
May I ask,
yeah.
are those 1, 2, 2, 3 fill-in brackets completely free, or there's somehow constraint also?
Could you repeat it?
So, okay, we impose the zeros to satisfy the constraints
Yeah.
for the first 2 brackets, and we say that we have some kinematics left in those brackets. They are not necessarily 0, but are they constrained? Are they completely free? Or
They're completely free.
Okay.
There are no further constraint on the undotted spinors in this case. Yes? Your question? Oh. Okay. So then, of course, we want to construct, since we want to have a specific dimension, so the only thing that we can do is to write the most general form of 3-particle amplitude with some Helistes H1, H2, H3. Maybe just we can write as some product of these okay, where these are some arbitrary powers, yes? Okay, that's the most general form of 3-particle amplitude, which you can construct by using this holomorphic solution, right? So now, what we can do is, what you do next is, well, we use the first, we use these constraints, and we use both constraints. Simply we rescale, for example, with a D2 plus D3, which you get by rescaling 1, will give you, we write to Helest number 1, yes? You rescale 1, you have D3 plus D2, and it's minus 2 times Helest 1. Yes? All right. Okay, and then you have another from dimension. Now, another you will have, okay, let's, so, yeah, okay, so we have, okay, let's for the moment ignore the dimension constraint. This is, you have 3 constraints of this type, which will fix the D's, yes, for each Heleste. So you find at the end that you find D1 is H1 minus H2 minus A3, D2 is H2 minus H1 minus H3, and then D3 is H3 minus H1 minus H2. Yes? So it's completely fixed. Yeah?
Are these relations just angular momentum conservation?
No. Momentum conservation I used here. Momentum conservation is done. And what I'm using the first constraint.
Yeah, I know.
Little group.
Yeah, but does it have anything to do with angular momentum conservation?
Oh, angular, yes, angular.
Yeah, that's
Yeah.
what I'm saying.
Yeah. Yeah, that's one way of thinking about it. Because again, the little group is to angular momentum. Yeah, that's true. All right. Okay, so now, so I can write now, so the next thing that I can do, let's consider a case of spin 1, 3 particles of spin 1, just for illustration. So, for example, if you have m, so we can all plus amplitude. And that, you know, there is the only thing I can write, something which is proportional to that. Yes? This will give you +1, this will give you +2, and this will, because it's the denominator, this will give you +3, okay? Then all minuses will be just 1, 2, 2, 3, 3, 1. Yes? There's opposite.
Or could be some constant in front?
What do you say?
Could be some constant in front of this expression?
Yeah, I don't care. For the moment, that will be important in a second. I started what time?
Well,
20, yeah?
Already a little bit over time, so you should.
Well, no, but I started like 20, yes? Like, I still have like 5 minutes, yeah, I guess.
So you're talking
Yeah.
for over and out now.
What?
You're talking for over and out now.
Okay, I'll finish that. Okay, that is very short. Okay. Then, so this is that. Then the other ones, I can write them here. It'll be amplitude in which you have 2 pluses and 1 minus, yes? Again, up to proportional, up to some coefficient, numerical coefficient, which may be some coupling constant, yes? For example, which come from the coupling constant, yes? Like in case of blue ones, it would just G, yes? So now, look, now it's easy to see, you see clearly that they have different dimensions, yes? Okay, so in actually to keep the dimension to be 4 minus 3, the dimension altogether should be of that, should be 4 minus 3, 2. C is for 1 lambda, so it's C has so dimension altogether should be 1, which means that there is only one case in which you won't need this scaling dimension from the coupling, and this is this case. This has dimension 1. Yes? So only amplitude, which is minus minus plus, for spin, for helicity, which is plus minus 1.
Plus minus?
Minus minus plus.
No, plus minus doesn't also have dimension 1?
That has dimension 1, because it is 1.
That one, but I think plus minus as well?
Which one? The last one?
No, plus minus.
Plus minus, plus minus has also plus minus also, so I have to use it. Let me check, that's true. Yeah.
Would there be bracket 1 to square?
No. It's, that is wrong. That is cube here. Yeah. Okay, it'll be a disaster. Okay. So only one has a specific dimension. So the only amplitude for spin 1 particles is this minus minus plus amplitude, the only holomorphic solution. Similarly, from holomorphic solution, the anti-holomorphic solution, of course, would have amplitude plus plus minus. Okay. And now, of course, in case of in Young-Mills theory, this is all gone. That could be amplitudes in some other theory. But the Young-Mills, in QED, yes, that could be an amplitude. It cannot be in QED, however. Why? Some amplitude loop coming from photon. Well, you see that if these are 2 identical particles, 1 and 2, yes? Okay? So you see that if you exchange 1 and 2, you get a minus sign here. This will remain invariant. So this amplitude is antisymmetric 1 and 2. So the amplitude as it stands, without an additional factor, cannot describe scattering process. So it means that there might be some difference, yes, between those two guys. And the only way to do it is to introduce some anti-symmetric tensor. Okay, so we have A1, this is 1, 2, 3, A2, A3. And there will be some coupling here. There may be some I factor or whatever. But the only way to make this amplitude satisfying, have a right statistics for gluons, is to have this 3-index antisymmetric object, which we'll identify with the structure constant of the underlying gauge group, right? So you see, to summarize, that these constraints coming simply from little group invariance, or we say from angular momentum conservation, and from dimensionality, really provide lots of information about scattering amplitudes, and then, okay, we will use it in the next time. All right. Any questions? Questions? You can construct, well, you have always 1/2, and 1. Yes, so.
Then we don't need this factor.
Hmm?
Then we don't need this factor, so it can be antisymmetric with this fermions.
No, for example, you can have amplitude in which you have a gluon decaying to gaugino, to like a supersymmetric theory, a gluon decaying to gluinos, and that will be non-vanishing.
Okay.
Yeah. Yeah, so you have to have another theory. You have 1/2, but I'm talking about pure angles. I'm talking about 1, 1, 1. It doesn't matter here at that level. Supersymmetry on another argument doesn't matter at all. All what matters is this little group plus dimension. Okay, no questions, you can go ahead. You have to take a break. What do you do now? You have a break?